Okay, at the end of the last video, we were talking about this rule for complementary events. The probability of something not happening is equal to 1 minus the probability of it happening. So for example, if the probability that it will rain tomorrow is 30%, what's the probability that it will not rain tomorrow? Well, that would be 1 or 100% minus 30%, so 70%. If a lottery ticket has a 1 over 35 chance of being a winner, what's the probability that it is not a winner? So the probability of it not being a winner is 1 minus the probability of it being a winner. So 1 minus 1 over 35, and to subtract the fractions, we can write this as 35 35ths minus 1 35th would equal 34 35ths. If you got a 1 in 35 chance of winning, you've got a 34 in 35 chance of not winning. A teacher estimates that there is a 0.92 probability that no one in the class will get the right answer to his super tricky bonus question. What is the probability that at least one person will get the right answer? So notice that these are complementary events. It's got to be one or the other. Either nobody gets it or at least one person gets it. So maybe nobody gets the right answer, maybe one person gets it, maybe two people get it, maybe everybody gets it, but it's got to be either that nobody gets it or that at least one person gets it. If at least one person gets it, that means it's not true that nobody got it. So the probability that at least one person gets it would be 1 minus the probability that nobody got it. Sorry, I had to fix that. So 1 minus 0.92 equals 0.08. Now let's talk some more about empirical probability. I told you that was one of the other ways that probabilities could be assigned. So empirical probability is where probabilities are determined experimentally or based on past experience, rather than by assuming that all outcomes are equally likely. So under empirical probability, the probability of an event is just the relative frequency of that event. It's what percentage of the time that event has happened in past experience. For example, consider the question, if a woman is going to have a baby, what's the probability that the baby will be a girl? The classical probability approach would be to assume that there are two outcomes, girl and boy. Treat them both as equally likely, and so the probability of having a girl would be 1 out of 2, 1/2. The empirical probability approach would be to look at birth records, look at a whole bunch of babies that have actually been born, and count up what percentage or what fraction of those babies have been girls, and take that fraction or that percentage as the probability of a baby being a girl. And if you do that, it turns out that slightly more than half of babies are boys, slightly less than half are girls. So the probability based on that empirical approach of a baby being a girl is a little bit less than 1/2, a little under 50%. Now here's my made-up example. Let's say that you drive to work every day on a route that takes you through 4 traffic lights. You have to drive through 4 intersections that have traffic lights. And if it's a really good day, they might all be green when you get to them, and you can just sail right through them and not have to stop for any lights on your way to work. If it's a bad day, all 4 of them might be red when you get to them, and you have to stop and wait for all 4 of them to turn green. And on an in-between day, you might have to stop and wait for 1 or 2 or 3 red lights. So on any given day, the number of red lights you have to wait for could be 0, 1, 2, 3, or all 4 of them. And so you could decide to keep track. And over 200 days driving to work, you keep track of how many red lights you have to wait at each day. So it turns out that on 10 of those days, and then 10 out of 200 would be 0.05, you didn't have to wait at any red lights. And there were 50 days out of the 200, which is 0.25, where you had one red light that you had to wait at. 72 out of 200, which is 0.36, or 36% of the time, you had to wait for 2 red lights. 52 days out of 200, which is 26% of the time, you had 3 red lights. And then there were 16 days when you had 4 red lights. That was 0.08. So we can take these relative frequencies as our probabilities. Like we could say there's a 0.08 probability that on any given day you'd have to wait at 4 red lights on your way to work. So what's the probability that on any given day you will encounter 0 red lights? Well, that would be 0.05 based on this. What's the probability that you will encounter more than 2 red lights? Well, how many is more than 2? Which of these numbers are more than 2? Well, 3 would be more than 2, 4 would be more than 2. So if you drove to work and you had to stop for either 3 or 4 red lights, you'd say, oh no, I had more than 2 red lights. So the probability of that happening would be, now notice that's a total of 68 days out of 200, or we could just add together the relative frequencies and say 0.34. On 0.34 of the days in the past, and when you were keeping track, you had more than 2 red lights to stop at. So you can say there's a 0.34 probability that on any given day you would encounter more than 2 red lights. What's the probability that you would encounter at least 2 red lights? Okay, how many of these numbers are at least 2? At least 2 red lights would be how many? Well, 2 would be at least 2, so would 3, and so would 4. Not 0 or not 1, those aren't at least 2, but 2, 3, or 4. So if we add up these relative frequencies, they add up to 0.70. 0.70, or 70% of the time, you had to wait for at least 2 red lights. So the probability of encountering at least 2 red lights is 0.70. And what's the probability that you will encounter at most 2 red lights? That means 2 is the most, but it might be less than that. So which of these numbers are at most 2? Well, that would be either the 0, the 1, or the 2. Adding those relative frequencies together, we get 0.66. So the probability of encountering at most 2 red lights is 0.66.